Welcome back. If you're in East Coast, it's a little past lunchtime, so hopefully you had a good lunch. And sorry we couldn't be on premises and provide you a nice buffet lunch, but that's the way it is virtually. I have the pleasure of being here at this time with two folks from Uber who are also involved with the Apache Hudi project. It's going to be a fascinating talk. They're going to discuss the Apache Hudi project, the streaming data lake platform, and the work they've been doing with that. And we have Svibalan Narayanan joining us. He's a senior software engineer with Uber and a member of the Apache Hudi PMC. And he is being joined by Nishith Agarwal, who's engineering leader at Uber and also a member of the Apache Hudi PMC. So Sribalan, please take it away.
Okay, cool. Thanks, Jill. Let me share my screen. Can you guys see my slide? Okay, cool. You guys hear me well, right?
Yep.
Okay, sounds good. Good morning, folks. Today, we're going to talk about Apache Hudi. We'll see how you can actually build like a streaming data lake over Apache Hudi. I'm Sivabalan Narayanan. I'm joined with Nishith Agarwal. Both of us are PMC in Apache Hudi, and we also work at Uber. Nishith actually heads the ingestion data platform in Uber, and he has also a lot of experience in large-scale distributed systems. I'm actually part of leading mobile networking stack at Uber, but prior to that, I have a data background as well, and that's why I'm part of Apache Hudi. Let's get into today's agenda. We'll start out with understanding different data processing modes in play in the analytical world, and then we can see what is Hudi and what are the key design choices we have made that it makes it conducive to actually build like a streaming data lake. In the next section, we can see what or how does a streaming on streaming means in a data lake world or an ecosystem. In the last section, we can see how we can actually build like a streaming data lake using Apache Hudi. There are myriad ways of doing processing on the data lake front. The first one is batch mode. So if you look at how traditional batch analytics were happening, so basically you take an entire batch from your, typically you have multiple different types of sources on one end where you replicate the data to your data lake. These includes raw events from multiple application services, database change logs, and so on. So from these, your tables in data lakes are generated or refreshed at regular cadence. But here, what exactly happens is that you take the entire batch of data and then you ingest into your tables in data lake. So this could, the cadence could be like few hours or even once a day because the data involved is very huge. As you can see here, even though the change is very like a factor of a smaller factor compared to the entire data set size, you need to actually compute the entire data set time and again. This is very slow and costly, as you could infer, because the ETLs of raw data is not as smart to do recomputation only on the delta of the data. So in a typical batch system, the execution models have different stages in play. But the problem in the batch model is that the stages are not pipelined in the sense like every stage had to produce the entire output and then give it to the next stage in the loop. Many times these intermediate data is actually spilled to disk and involves an operation of moving around the data like shuffling. So the programming model, coupled with the fact that you'll have to collect the entire batch of data and compute the results for your use case process data freshness concerns, preventing us from providing any real-time data freshness guarantees. Given the batch systems tend to process large amounts of data at once, these are generally costly due to large memory and compute requirement required to carry this job. Since you are writing large amounts of data, write latencies are actually higher since there isn't unlimited compute resources available. Typical examples for these batch systems on the cloud are Spark, Hive, and Presto, which power popular use cases like building dashboards, generating offline reports, payrolls, and so on. So the next mode we have on the data trend is incremental on batch processing. This is what Hudi is based on. That's how it started. Hudi gives like incremental primitives over batch data. In other words, you can apply only new inserts, updates, or deletes to your existing data in your data lake without needing to rewrite your entire table or partition. This means that you can have your ingestion run once every few minutes and take the delta and apply to your tables in data lake. Similarly, for all, if you have a chain of ETL pipelines, a lot of different derived tables like bronze, silver, and gold, all these pipelines can do just delta applying to your sync table. As it's evident, there's an order of magnitude faster and cost-effective compared to traditional batch analytics. Hudi also handles late arriving data, so you don't need to miss out on any data or wait for another half a day or 8 hours to actually catch up. So in recent years, there have been a great deal of advancements in recent programming paradigms and execution models in large-scale data processing landscape. Different use cases demand different features and guarantees. In general, many systems have emerged to solve them. The streaming programming model in particular has unlocked a lot of interesting use cases and has provided a paradigm shift from batch systems. At a high level, there are fundamental advantages of using streaming systems. Streaming systems work on a record basis, streaming data continuously. Generally designed for working with unbounded streams of data. If tapped into this record by record processing, data freshness is really, really good. Given it's processing smaller units of data when compared to the batch systems, and as pipeline architecture, which facilitate concurrent processing of different stages, it's really, really fast. Since computations happen over a smaller set of data, not only can be cost effective, but it's also more reliable because larger jobs tend to fail. There could be some nodes which are going up and down. You need to restart it, but in streaming, you don't have such an issue. Some examples are stream processing systems or Flink Kafka streams that power business critical use cases like fraud detection, cybersecurity, to name a few. So this is just a sneak peek of the comparison between batch and streaming. Typically, your latency for writes are greater than 5 minutes, up to the order of 30 minutes, or even greater depending on your architecture or the underlying system you use in the batch. On the streaming side, typically it's less than 5 minutes. So the write amplification will be higher in the batch mode as you end up taking in large amounts of data and then rewriting the large amounts of data on the sync as well. But on the streaming side, the write amplification is lower because you're just applying the you're operating on the record basis, and then you're just taking the delta over there. Update cost is again higher on the batch side due to the same reason, whereas in the streaming side it's lower. When it comes to table services are something like which happens in the background, like cleaning, compaction, or anything of this sort. On the batch incremental side, you can afford to do sync or async because you can afford some leeway on the latencies. Whereas on the streaming side, you can't afford to do a synchronous table services because your data freshness requirement or the latency requirement for streaming is actually very, very fast. So with this, we would like to introduce Apache Hudi, how Apache Hudi solves big data analytics problem. So Hudi stands for Hadoop Inserts, Deletes, and Incrementals. Hudi was an original pioneer in the transactional data lake movement. You could even find articles in O'Reilly in 2016 on the need for incremental processing of big data from the creators of Apache Hudi. Apache Hudi was introduced in Uber as a distributed database abstraction layer over DFS. It provides a unified and optimized analytical storage at scale. Transactional updates or deletes for big data or even unheard of back then, which was offered and popularized by Hudi. We also introduced incremental pull framework for major data sources like Kafka, Hive, CSV, etc. So as I mentioned, Hudi was introduced in Uber during late 2016. From there, it has grown leaps and bounds and powers one of the largest transactional data lakes on the planet. We operate over 150 petabytes of data for 4+ years, spanning 8,000 tables. There are different query engines in play depending on the usages, ranging from Spark to Hive to Presto, Vertica, etc. Hudi crunches roughly 1.5 petabytes of data on a day-to-day basis to keep the data moving and available for consumption. It wouldn't be an understatement to say that Hudi is very critical for Uber's data in all walks of life, ranging from analyzing experiments to visualizing business trends, running machine learning algorithms, or taking any key business decisions. So we'd like to dive into design choices right away. What are the design choices that Hudi made to actually make it streaming friendly from the get-go? So this is a very high level, like a 10,000 feet view of Hudi, where you have your data, and then in the Hudi storage component you have data, you have index, and then you have metadata, and then querying is actually going to consume from this. But if we actually zoom in to understand how the data layout looks like, typically tables are partitioned into multiple partitions using different partitioning schemes. Within a partition, Hudi has a concept of different file groups. So a record will always belong to one file group. So the updates and deletes actually can be applied to the same file group where it belongs to. So when a write comes in, it looks up the index to understand where exactly the record should go into. If it doesn't exist, it automatically figures out where to actually, either it could go to an existing file group if the size hasn't met. If not, it will create a new file group. But updates and deletes, it automatically figures out where because of the index we have. Also, we have a timeline and metadata table to keep track of all the actions that's being taken on the table. So having given a sneak view of the storage format layout, we can take a look at the design goals or design choices we have made. So Hudi design fundamentally unlocks streaming style parameters for underlying engine. Either it could be batch or streaming. These parameters such as upsert or deletes are optimized and implemented with record level changes in mind. This required some fundamental technology such as key-based operations or fast record level processing. Other core design choices in Hudi is the ability to perform frequent commits as needed without overloading your system with metadata, which Nishit will be covering partly in the later part of the slide. So we embrace a log-based design, which actually facilitates record level updates and partial updates, and building a system that minimizes overhead of such frequent commits that are all baked into Hudi's design. So if you don't have a log-based or a key-based design under the hood, it will be very tough to apply streaming primitives on your data lake in general. To show you some of the key design goals more deeply, Hudi allows you to manage record level metadata. So per record metadata over, we prefer per record metadata over file level, because if you're planning to do like a diff over file level or entire snapshot comparison, it's going to be costly. Per record metadata makes it very conducive to write streaming pipelines with engines like Flink. With Hudi record level merges, it's more easier and feasible. For example, you could log only partial updates with just the changed columns and let your merge logic take care of merging with the previous versions of the record. This results in drastic reduction in write amplification in data lake. Hudi embraces file group design, as I mentioned, we went through the previous slide, which makes it easier for CDC-friendly use cases as well. Once you retry, you could able to retry old new values, or even you could retry all values depending on your use case. You could also do point lookups or do time travel as per necessity. Next critical design choice is the record level indexes. This is synonymous to state stores if you're familiar with the streaming engines. So where you store some of your states. So Hudi has a record level indexes, it's pluggable. There are multiple indexes available to you, or you can come up with your own index. So the indexes actually maps keys to file groups and assist in applying delta or doing incremental updates to your existing data. So as I mentioned, Hudi has a concept of file groups. Within file groups, we have data logs, which is columnar format, optimized columnar format of Parquet, or you can bring your own format too. Also, we have something called delta logs, which are maintained at a file group level, which actually have just updates to the existing file slices. Since each file group is bounded in size, there is a bounded overhead with respect to your metadata size. and you can actually control it depending on the size of the file group you define. You could leverage append when cloud source supports it, which again results in lower metadata as well. And especially keys are mapped to the file groups. Mergers actually are very local or confined to each file group, and hence bounds the merge cost as well. For example, if your record keys are random, completely random UIDs, you might be forced to do a global update if not for these mappings. With Hudi, we are proposing to use the incremental processing model on streaming engines. This can help bridge the gap between batch and streaming models. For batch, Hudi's incremental model, as pointed out earlier, was a game changer, using streaming primitives and treating batch as unbounded streams. Once the primitives are available, using streaming engines brings not only the benefits of incremental processing, but also uses the rich programming model of streaming that opens up many possibilities, such as using watermarks, state stores, etc., that can supercharge things you can do. For example, with the incremental processing and streaming model of watermarks and state stores, you can perform stream or stream joins while performing ETLs. With this background, I will hand it over to Nishit to show you how to build a streaming data lake using Hudi.
All right, thanks, Siva. Let's see. Yeah, can you see my screen? All right. So yeah, so let's look at some of the advances in the stream process and batch process unification. So there are many popular engines out there now. Some popular engines approach to data processing from different angles. Flink, which is quote unquote like become sort of the streaming platform, approached from a streaming perspective, but soon developed rich APIs for batch data and ultimately providing a unified approach to data processing. Spark, on the other hand, began with some sort of like heavy batch processing, but ultimately supported this mini batch streaming model on data, thereby claiming that they are also a unified processing engine. Beam, which is from Google, on the other hand, is also a rich programming model, which is agnostic of underlying execution engine, proposing again a unified programming model on batch and stream. So the takeaway from this is, most of the popular engines for data processing, allow you to switch between batch and stream processing very seamlessly. And this is just to cater to different use cases, but not create different stacks as you solve your business critical problems. So, with batch and streaming comes a natural question, how to trade off completeness versus latency. So how long should an application wait to get accurate data, the view of the data in arrival time order? Different applications make different choices. Dashboards, business signals might require low latency, which use streaming solutions. While batch is best suited for large jobs, for example, ML trading algorithmic jobs, which require you to have a lot of data to be read together. Although although there is a realm of these use cases in between, which don't want the latencies of batch, but also don't want to suffer from the lack of completeness that streaming solutions tend to incur. So there is where we have these engineers and analysts who want to build dashboards, reports, or even trigger mechanisms, or there could be product managers that want to analyze some of this data in real time. So in general, the requirements from each of these sections differs. For just like we talked about, critical ML flows like fraud detection need fresher available data, while generating some historical report, there is some leeway for data freshness. So how do we solve this problem where the stream processing frameworks are saying it's okay to switch between your data processing, but ultimately when the data lands onto a storage format or a disk, we run into these problems of completeness, latency as other consumers consume this data. And so generally, this is sort of the landscape right now, quote unquote referred to as a Lambda architecture, where you have a bunch of data incoming and based on your use cases, serving different kinds of personas, different choices are made. So for Flink, for something which requires, a event-driven architecture, Flink is the popular choice, or in some cases, Spark streaming, where you consume data, you fire an event to a system that needs to take an action, and then there's some state stored as part of that particular job. On the Spark side, like, large batch jobs do batch processing from sources and, write this data onto tables, just like how Siva pointed out. In general, this is referred to as your raw data, right? And generally, there's like some kind of a data engineer who's doing this, kind of like, understanding different kinds of programming models and maybe even supporting both. Once you go further downstream, this data needs to be consumed, maybe needs to generate further tables which are curated, especially, for example, for machine learning algorithms. And again, like as we talked about, this data can be large, and the more pipelines that consume this data, they need to do some kind of batch processing. And then once all of this is done, maybe there are like other derived tables also created. And once all of this is done, ultimately an analyst or a person who's consuming this data via query engine is able to like consume this data. So that could be batch, could be query engines that fire off batch queries. But at the end of the day, as you can imagine, like this end-to-end architecture, it's quite complicated. There is no unification on storage, and there is definitely delayed freshness. And so if we have this paradigm of batch and streaming, do we have with the programming model that Shiva talked about, that Hudi proposes, of providing stream primitives, can we do better? And that's where Hudi comes along and allows you to build a data lake, which is basically a streaming data lake with this unified storage format. Right? So you have your traditional pipeline, which has a source of data incoming. Now, the interesting thing is, you could now use Hudi along with any stream processing engine such as Flink or Spark streaming to not only do actions on your data, such as firing events, but also use the stream processing primitives from Hudi to be able to write out your data into tables, right? And then since these are all, Hudi is all based on stream processing primitives, you can not only write out your data into your raw data in streaming manner, but also consume this data for your downstream tables in a streaming manner, right? So, and all of this is possible because of the record level design that Shiva touched upon, providing CDC at record level, right? Now, all of this is great, but this becomes a challenge when you actually write data so fast into and in small quantities onto the data lake. And so you need a bunch of table services that you see at the bottom to be able to manage your data lake. And they do different kinds of activities, which I'll go over in a bit. So, so if you think about this now, you have, an optimized storage format that provides stream primitives, and you have it being engine agnostic, but that's not enough to build a data lake platform. And, like Hudi itself is proposing that it can actually allow you to build an entire data lake platform with its primitives, right? So let's look at what are the necessary components of this platform, right? So firstly, as described before, a storage table format. From its storage table format perspective, Hudi Data Lake supports a log-based model that allows for us to build streaming primitives. So from a storage perspective of being able to ingest data, we're good. But once your data is written out into these data systems using Flink, it causes this explosion of the number of files. So, we provide, like, the Hudi platform provides services such as compaction, clustering, cleaning, and archival to be able to manage this data for you. So let's look at each of these a little bit in detail. So what is compaction, right? So the compaction service is used to convert a row-based format data into a columnar format. So data lake query patterns are generally scan-based over a small subset of columns on a single or maybe multiple tables, depending on if you're doing joins. But for streaming writes, row format is the best suited for fast writes, right? And as we talked about, Hudi works with record level changes as well. So we need a system to meet this impedance mismatch to satisfy both use cases for you to be able to ingest streaming while not cause this explosion of query latencies because of the impedance of columnar versus row format analysis. Additionally, with streaming, data writing continuously can generate a really large number of small files, right? And from what you may have used, small files tend to kill sometimes your distributed file system because there's just an explosion of metadata, or it may kill your query performance because generally queries perform better when there are lesser files to read. So again, here to meet this impedance mismatch, we need a table layout service that can continuously look at the table layout, suggest better ways to improve this query performance, and then ensure that there is no degradation for the entire system. Right? So one of the ways to actually improve this, for example, is to stitch files together. Hey, like, is there a service that can in the background understand what is the right file size for my query pattern? Additionally, there could be use cases where your ingestion pattern is very different from your query pattern. And you want to move around data very differently for your queries as opposed to how your ingestion is writing your data. And so you may want to, like, for example, sort your data in different orders. And clustering service that is provided by the Hudi Data Lake platform lets you do this. A couple of other services that I want to talk about are the following. So one of them is cleaning. Now, think about ingesting change data capture from your upstream tables, which has updates and deletes. So this could be your business critical tables lying in MySQL, Postgres, your favorite traditional transactional stores. Hudi uses MVCC to support features such as ACID, time travel, whenever it's applying updates and deletes onto these particular tables. But all of this comes at a storage cost, right? What if you wanted a service that can expire and TTL your old data and then clean up and keep your data lake healthy, right? So cleaning is that service that Hudi's data lake platform automates for you. The last one that I want to touch upon is the growing number of small. So as you write more and more data at a petabyte scale, metadata again becomes sort of a data problem, right? And Hudi's table format provides a timeline of such actions that are happening on a table so that you can go back in time and say, hey, what happened to my table on my data lake? But having such infinite retention of metadata comes again at a cost, right? So to ensure we keep older information, but again, not let metadata file explosion because you may want this data for auditing, Hudi provides an automatic service called archiving that's periodically runs and archives this metadata into some archive location where you could later go on and check, hey, like, what happened to my data? Did I do something wrong with this data in the past and things like that? And the cool thing about this whole platform is all of these services can run asynchronously along with your streaming jobs. And this is what Shiva covered, that in the streaming primitives, if you're looking for like minute level latency, you can't have these synchronous jobs run as your ingestion is happening. So finally, I want to last couple of minutes, I want to just quickly go over some of the code snippets. How do you run this in production? We've talked about some of the architectures, but what about getting into a little bit of the details? So the most popular way to use and build this streaming data lake is using the Hudi DeltaStreamer framework. So this framework, running this framework is as simple as described in this slide. You download the bundle jar that the Hudi platform provides. You plug in your favorite source, maybe it's a Kafka source, and then you say, hey, I want to run this in a continuous mode. And that enables a managed async compaction and cleaning along with doing streaming writes, right? So you can actually build a streaming data lake without writing any code, just with this particular setup with custom configurations that you may want. And in the future, we are working on having managed async clustering and archival as part of this platform. So, obviously we talked about, different kinds of streaming engines. So if you want to run it, custom made, you don't want this like platform to manage it for you, but you want to like run these services in your own way using different, infrastructure that you may have. You can use a Spark streaming job to write data like this. And then you could, use the higher level APIs of the Hudi platform to schedule any of those table services in asynchronous manner. And finally, a sneak peek into Hudi on Flink. There's a lot of work recently done on providing Hudi as dynamic tables on Flink, which enables a bunch of cool use cases that that build on the Flink programming paradigm. And if you want to know more about the Flink implementation or how to like start using it, there's a nice quick start on the open source website that you can follow. Right, so like going over the community a little bit, Hudi is adopted widely by many companies, large and small. Some other large-scale deployments outside of Uber are at Robinhood, Alibaba, Amazon Web Services, to name a few. And as you can see, there are like many other companies that have adopted Hudi. So the point is, it's like a very battle-tested platform that is used by many customers. And at this point, I would encourage. All right. At this point, I would encourage you to check out the community. We're super excited to grow this community. We encourage you to try building your data lake using Hudi. It's as simple as I pointed out in the slide. There are many ways to engage with the community through Slack, mailing lists, GitHub. You can follow us on Twitter for the latest and greatest features that are upcoming. Right. With this, thank you so much, folks. We can take any questions at this point.
Thank you so much, Nishith and Sibalaban. This has been a great presentation, a great introduction to Hudi, and this is definitely a great platform, a great tool to be used with the proliferation of data lakes we're seeing across organizations. We invite our audience to participate, to ask questions. Just simply type your question into the box at the right of your screen, and Nishith and Sibabalan are standing by to answer your questions.
You can refer to Shiva Balan as Shiva. That's how he goes by. So it's
Shiva.
easier.
Yeah, Shiva is good.
It's easier
Okay,
for me
my
as well.
apologies. My apologies
Yeah,
for butchering your name. Sorry about that. Okay, great. I'd be curious. At Uber, how's it being used at Uber? What kind of application, if it's okay to mention, an area where it's being employed?
Right. Yeah. So at Uber, Hudi powers actually many different use cases. So the bread and butter use cases is the entire data lake is built on Hudi. Right. So we have about 250 petabytes of data that's managed by the Hudi data lake platform. But on top of that, the kinds of use cases that it enables are, we have, for example, whenever you build machine learning pipelines, one of the challenges are, hey, like if data is changing upstream and I want to update my feature set, how do I update my feature set without actually reading the entire data and re-snapshotting that? That becomes like a really costly process. And if you have, we run data models for Uber Eats, which are like massive, hundreds and hundreds of terabytes, and like consuming that data becomes tricky. So one of the ways where Hudi is being employed is, hey, can we make all of this incremental, right, with all of these primitives? Another use case is around earnings. So as we go through like all of these different kinds of like use cases, that like business use cases that Uber has, exposing different data to different customers, to different users, how do we do that in an efficient way, right? Like how do you point out exactly where the data lies and then be able to like expose this data? Again, like record level indexing, all of these things help immensely in those kinds of use cases.
Okay, fantastic. And I'm curious more about the role of Apache Kafka and Kafka streams. Many organizations have turned to Kafka Streams, of course, to address streaming, real-time streaming data. You know, is this does Hudi integrate with the streams, or does it replace it in some cases, or what's the interface, the interchange?
Yeah, so I mean, right now there is like not like, I think the way Hudi looks at is, if there is a execution engine, I can be agnostic of that execution engine, but otherwise I need an API to be able to pull streams. So generally Hudi will connect to Kafka directly and pull streams. Kafka Streams itself is also an execution framework, I think, like Flink, but it has some custom semantics. And right now there is no support for like running Hudi on Kafka Streams, but we are looking at providing, you know, sort of connectors that may be able to do that.
Okay. Okay. Powerful stuff. Powerful stuff. Okay, great. Will you folks be available in the networking chat room? If we have a networking area, our audience can click on the left-hand side of the screen to join. If you're available over the next few moments to chat further with our audience, that would be great. Otherwise, the audience members can chat among themselves and exchange ideas and their perceptions. With that, Nishith and Svibalan, this has been a tremendous presentation. A lot of good information here. It's been great learning about Hudi. This is something companies need to look into and understand. There's a lot of potential here. So we thank you very much for joining us today.
Thank you, Joe, for having us.
Thanks a lot, Joe. Yeah.